Assalamualaikum and good day again. We will start with some revision on couple first, and then we'll look into the question that I posed in WhatsApp. So let us begin. So we have established in the last lecture why moment exists. So basically, if we have a force that is along the line of or along the point of moment, for example, we have point A and B. If the force pass through the point of moment, if we want to find moment at A, so moment at A due to this force will be equal to 0 means F pass through point of moment. Okay, or in other words, we can also say D is 0. Okay, perpendicular distance from the line of force towards the point of moment is 0. Okay, so that's why moment at A equals to 0. Or to make it simple, if the force pass through the point, the moment will be 0. It doesn't matter what's the direction of the force. The force can be directed towards the point or outwards from the point. It does not matter. Moment equals to 0. So this is clear. We have also established that if the force is at any arbitrary location respect to the point of moment at certain angle, in this case, the force can be decomposed into two components. One is passing through point A. So this component of F, let's say F1, and there's another component of F2. We are saying that F is equal to F1 plus F2. So moment due to F1 will be equal to 0. Okay. Okay, so I'll let be just the magnitude of it. The moment due to F1 is 0, while moment due to F2 is not 0. And if we are taking positive clockwise convention, so F2 will create a moment that is negative F2 times AB. Okay, so everyone is clear about this. So F2 will create a moment counterclockwise, and since we are saying that moment is clockwise positive, so it is a negative moment. And moment due to F1 will be 0 since F1 is passing through A. Okay, so we have decomposed F into F1 and F2, right? So this is clear. Let's say we have more than one force. Let's say this F at B, and then we have another force. Okay, we have another point here, point C. This force is FC. Again, at any angle. This is theta 1, theta 2, for example. Okay, it does not matter. The main point is the summation moment at A must be coming from both FC and FB. And in this case, if I'm taking again our convention to be positive clockwise, so summation moment at A will be coming from these two forces. Let's say I consider FC first. It will be equal to FC cos theta 2 times AC. And since the moment due to FC is positive, it is creating a clockwise rotation. So we give a sign positive there. And then we have FB that is causing a counterclockwise rotation or giving a negative moment there. So we have FB cos theta 1 times AB. So this is the moment at A. Since we have two forces, it will be the sum of moment coming from these two forces at A. Here we have a pin joint at A. To be more general, we can also remove this pin joint. Pin joint does not need to be there. The purpose I have pin joint here just to state the obvious that, okay, the whole thing is rotating about point A, right? We can have this rigid body, okay, without any connection. Does not matter, okay? It does not have any support. We can have the same point as well. Let's say A, B, and C. And if we apply FB again, angle of theta 2, and another FC at angle of theta 1, we still get the same moment at A, which is FC cos theta 1 times AC minus FB cos theta 2 times AB. Okay, we still get the same moment. And this moment is not 0. Okay, why it is not 0? Since both of them not passing through point A. Non-zero. Okay, this is clear. Now, what happens if suddenly we have specific conditions for these two forces here? Okay, what do I mean by specific conditions? Instead of having something like this, we say that, okay, both of these, we say this is F, B, and the magnitude is F. this theta. Okay. Why I call this FB? Because this is the force applied at B. Okay, let's say the magnitude is F. Some arbitrary value. And we have another force here, force at C. However, in this case, the magnitude is also F. Or to avoid any confusion, let me give number here. This is 10 Newton. Also 10 Newton. The angle of FC is also theta. In this case, what we have is two forces with parallel lines of action. Okay, these two lines are parallel. Why parallel? Because they are having the same angle theta. Okay, with respect to, oh my bad, the angle is not like that actually. This angle theta. Okay, they have the same angle with respect to this axis. Okay, and this axis is also parallel to each other apparently. Okay, so basically we have two forces acting along parallel lines, and not only that, both of them is having the same magnitude. Okay, the same magnitude. So we have this, right? Now we want to see what would be the moment coming from these two. Okay, so we will adopt the same moment equation. At A, the moment will be equals to, let's say I consider FC first. So plus FC cos theta times AC, alright, minus FB cos theta times AB, right? This is what we have. Okay, moment at A. Now let's say, in this case, quite difficult to visualize things because we don't have numbers here. We can't see whether it is the same or not. I'm gonna replace this AB and AC with a number. So let's say AC is 2 meter, BC is also 2 meter. Okay. So moment at A due to these two force is equals to 10. We can leave the cos theta, or we can give a number to cos theta as well. Let's say make this more simpler. This theta is equal to 60 degrees, right? So cos 60 degrees is 0.5. AC will be 4, sorry, 2 minus 10, 0.5, 1. Okay, so here you'll end up with 5, 10 minus 5. So you have 5 Newton meter. Okay, so this is moment at A. Now let's see if we do the same moment calculation, but now at different points. So let's say we consider point C. Our forces are still the same. Now we want to find what will be the moment at point C. This force is acting at C, so there will be no moment coming from this force. So we just need to consider this moment, or FB only. Alright. So moment at C will be equals to FB cos 60 degrees times distance, in this case 2, right? And in this case the moment is rotating counterclockwise, so it's negative sign there. Here we have positive sign. Okay, minus 10. Did I miss something? Oh yes, My distance are wrong here. Okay, for AC, it was supposed to be 2 meter. That's correct. For AB, it was supposed to be 4. I wonder. So this will give us 10. This will give us 20. So 10 minus 20, you have minus 10. Now it makes sense. Okay. So we have calculated MA, giving us minus 10 Newton meter. We have calculated MC, also minus 10 Newton meter. In fact, we can move on to, let's say we want to calculate moment at B. Obtain the same convention, positive clockwise. Moment at B is at B passing through B, no moment. So we have only moment coming from C. So at B, FC will create counterclockwise rotation again. So we have minus FC cos 60 degrees times the distance from B to C. So we have BC there. So here is minus 10 times 0.5. BC is 2. So here we have minus 10 again. Right? So if we look at the numbers, okay, we are getting the same numbers even though we are doing the measure of moment, or we are calculating the moment at different point. Okay, so moment at A will still give us minus 10. Moment at C also minus 10. Moment at B is minus 10. But we can do the same calculation anywhere. At this point, or in between, it does not matter. So this tells us one thing, which is the moment due to these two forces will be the same anywhere. Okay, so moment due to these forces are the same anywhere. Okay, not just that, it is no longer point dependent. Okay, so the moment is not point dependent. Previously, our moment will depend on the location where we take our moment. Now, no longer point dependent, provided that we have these forces. Okay, and these forces should be forces with equal magnitude, opposite direction, and along parallel lines of action. Okay, so once we have this condition met, we will have what we call as couple, or basically people also call this guy as free moment, because this moment is free from location. It is applied on the rigid body itself. Okay, anywhere we will still have the same moment. Okay, so in order to have couples or free moment, we need to have a pair force, and these forces should have equal magnitude, opposite direction, and parallel lines of action. Okay, so once we have this, we will have a couple. All right, what's the use of this couple anyway? Let's say we have the same rigid body with the same points as well, ABC, right? At B, we apply cos F, right? At B. Now we want to see what's the effect of this cos F at A, for example. Okay, let's say we don't know, right? But what we do know at A, there are no force, right? No FB acting at A, but we know the summation of force here goes to 0 since there are no force. So mathematically, it is correct if we put FB here, and at the same time we put another FB here. Okay, even though FB is not acting at A, mathematically it is correct if we have two FB here, because the summation of these two FB is equal to 0, which gives us our previous condition whereby we don't have any force acting at A. Right? We can do that mathematically. And not only that, we are seeing that this FB, this FB now is a couple. Okay, they are having equal magnitude, opposite in direction, and acting along parallel line of action. So this and this now become couple. All right, and when they becomes a couple, what happens now? Instead of having two forces here, you can remove them and replace these two forces with their effects. Basically, what these two forces do, they will create a moment, and that moment is not any arbitrary moment. It's a couple, which is not point dependent. It is body dependent. It is being applied for the whole body. So we have this as our free couple, and the magnitude of this free couple will be equals to the force times d. Okay, and this d is actually distance between the parallel lines. Okay, is distance between the parallel lines of action, or distance between the force. Okay, so here if we extend the lines, we will get this as our d. Okay, distance between these two parallel lines. Okay, these parallel lines will continue on forever and ever, of course. So this will be the distance, and of course we can say this is perpendicular distance between parallel lines. Yeah, also correct. Okay, or the shortest distance, also correct. Okay, in simple terms, it's just distance between these two parallel lines. Okay, don't tell me the distance should be at an angle of beta between this line. Okay, this doesn't make sense. Normally when we say distance, it should be this. Okay, which is 90 degrees respect to the lines, right? This one is not the right distance. Okay, so we know this moment is a free couple. Okay, so this guy, the couple of free moment. All right, and it is not acting at A, E, or B. It is acting everywhere. Okay, for the whole rigid body. So in that sense, when we go back to our initial problem, okay, our initial problem is we have force applied at B, right? This is our initial problem, right? And we want to know what's the effect of this force at A. So the effect is the same as if we take this force, put it at A, and then we add the effect of that force in the form of free couple at A. Okay, and this guy is equal to FB times D, and that D is distance between the parallel lines, or in this case, D will be distance from. Okay, in this case, I accidentally have my FB at a certain angle there. Okay, to make it more simple in terms of visualization, my FB is horizontal, certain angle, theta. Okay, fine. So this will be the line of FB, point A. So this will be our D. Really, okay. So we can have this FB flat at point A. Okay, and this representation is what we call as equivalent force couple system. So we have this as our original system, or original way of applying the force. We applied force at B. Okay, at A we don't have any force, but when we apply this FB at B, A will feel this. Okay, this is the equivalent effect of applying force at B. Okay, why we want to do this? Why we want to look at the force at A? For example, if I want to give you one example, it could be something like this. Let's say this is front view of a 747. This is the wing, right? And you have at the wing one big engine attached to it. Okay, and this engine has weight, right? And you are tasked to design a connection between the wing and the tubular body of this aircraft, right? And you want to know what would be the sizing of bolts that are needed to attach this wing to the body of the aircraft. Okay, so you want to know sizing of bolts to attach the wing to the aircraft, right? And sizing of bolts, that means you want to know what's the diameter of the bolt, right? Of course, the higher load will require a bigger bolt, right? So that means you need to know what will be the loading on the bolt. Okay, so that means you want to know what will be the effect of this, what will be the effect of the weight at this location. Okay, so to do that, we will transfer this weight to this location. How? Through our equivalent force couple system. So instead of having the weight here, we transfer the effect of this weight here. So what we have the weight and also the effect of the weight to this point. Basically what this weight do, this weight will create a moment about this point. And this moment is our couple of free moment. And it is equals to weight times the perpendicular distance from the line of force, okay, towards our point of moment, so this is our D, right? So this moment now equals to weight times that D. Okay, so our bolt here need to withstand this weight here and also this moment. Okay, any question, guys?
Sir,
Yep.
if there are two different forces, so this means it's not a couple.
If we have two different forces,
Difference. Yes.
okay, to be more precise, let us try it out. Okay, let's say for simplicity's sake, I'll have force at B equals to 10, which is horizontal. Okay, and C, again for simplicity's sake, I'll have this force like this. Okay, this is 90 degrees with respect to this AB or AC line, and the force here is also 10. Okay, so the angle here, let's say we have also simple angle here, 60 degrees. Okay, so this is 60 degrees. So we have 30 degrees, 60 degrees, 30 degrees. Okay, hopefully you can see the angles there. Right, once we have this, now we want to calculate what's the moment for point A, B, and C, just to prove the point. So we start out with point A. Okay, so at A, we have moments coming from FC and FB. We start with FC first. So we have 10, since the rotation will be clockwise due to FC. So it's plus sign here. 10 times the distance, then should be perpendicular distance. So we know this is perpendicular. So just times AC. Want to make it in terms of equation. So we have plus FC times AC. And then we have minus FB cos 30 degrees times AB. Alright, and if we substitute the values, we have 10 times, okay, A is 2 meter again, BC is also 2 meter. Okay, so this is times 2 minus 10 cos 30 degrees times 4. Okay, so we can calculate this. 20 minus this is 40 times 0.86. Can somebody calculate this first for me, please?
Negative 14.64. So
Negative 14.64 millimeter. Okay, fine. We'll prove later on whether this is correct or not. Okay, so we can do the same. We're taking moment at B. Okay. FB is passing through point B, no moment there. Okay, so the only moment is coming from this FC. Okay, so moment due to FC at B will be equals to, since it is rotating counterclockwise, minus FC times 2. So we have minus 20 there. Something is fishy here. Is it? No, it's not fishy. That's really the right answer. Okay. Moment at C, okay, will be due to FC and FB. FC will give 0 moment at C. Okay, so moment will be coming from FB only. So moment at C will be equals to, again, this moment will create rotation counterclockwise. This is equals to 10 times, I'll make it in terms of equation first. FB cos 30 degrees times BC.
negative 17.32.
20.32 centimeter. Okay.
Mm-hmm.
All right. So what's happening here? We have MA equals to minus 14.64. MB now minus 20. Okay. While MC is equals to minus 17.32. In fact, you can go on, try to find moment at different points here, or anywhere else. You find out that the moment values will be different and it will be point dependent. Okay, so all of these are point dependent. All of these are point dependent moment. So MA will be different with MB, will be different with MC, and so on. So MA is not equals to MB. Generally, they will not be the same. Okay, this is not a free couple. You cannot put MA at B or MA put at C. Doesn't make sense because their values are different. Clear?
Clear.
Okay.
Yes, sir.
Of course, we can also extend this couple to 3D space as well. Okay, so for example, if you have 3D forces, say F like this, do the vector operation. So moment at O, for example, is equals to the position vector RA cross with the force. You'll end up with the same answer anywhere. These two forces represent a couple in 3D space that will give you a moment that is point dependent. Okay, so when it is point dependent, you can put the moment anywhere on top of that rigid body. Okay, it tends to move the whole rigid body. Okay, that's what we meant by this free couple, or that's the effect of this free couple. That's just like our for example here, the free couple actually tends to rotate the whole wing. Okay, this weight tends to rotate the whole wing. by a counterclockwise rotation. Alright. So once we are clear with that, we can look into the exercise that I've given to you guys. And I believe very simple, right? Anyone succeeded in solving both within the time given? Hopefully, you can solve both questions within the time given. Normally, one question like this should take you 20 minutes to solve. Okay, so you have to time yourself. You should be able to solve one of these questions within 20 minutes, right? Because normally during your 1 hour test, we have 3 of these. Okay, so 1 hour is 60 minutes, so each one need to be solved within 20 minutes, right? So for example, in this question, we want to find what will be the equivalent force cover system at point A. So basically, to do that, we have to move all the forces point A. Okay, and if the forces are more than one, okay, not just 1 point, and not just one force. Let's say if we have only 180 Newton, we can just put 180 Newton at A and done. However, in this case, we have more than one force. We have 3 forces here. So we need to find the resultant of these 3 forces at A. Okay, so that's what I did here. So we need to find what will be the resultant at A. And since we have 3 forces, I'm using rectangle component method here. So I resolve everything along X and Y. So along X, we get RAX equals to 30 Newton. Along Y, we have RAY equals to 100 minus 109.81. So once we have this, we can get RA from its resultant along X and Y. So RA is just RA squared, RAX squared plus RAY squared. Sum of that square root, you have RA. And theta can be obtained from RAX and RAY. So in this case, I'm looking at this angle, which is from the horizontal axis. So theta will be tangent minus 1 RAY over RAX. So we have theta equals to 74.72 degrees. Okay. So this is just like what we have learned so far when we talk about resultant of forces. This is also resultant of forces. Okay. Just that we use that concept in determining the force within equivalent force cover system. After we done that, we have to calculate what would be the effect of moments coming from all these forces at A. Okay, so we have to find the summation of moment from all these forces at A, or basically summation of moment at A equals to what? So to do that, in this case, that the angles are pretty simple. So the first one is 180 times the perpendicular distance. The angle here is 90 degrees, so that means AB is already the perpendicular distance for this 180 Newton meter force, 180 Newton force. So we have 180 times 0.2. Rotation is clockwise, following our convention, so it's positive. And then for 150, this is the line of force. The line of force. So the perpendicular distance will be this distance, which is 0.2 plus 0.4 cos 30 degrees. So that's what we have here, 0.2 plus 0.4 cos 30 degrees. And then we have this free couple here. And since this free couple has free moment or a couple is rotating clockwise, so you can just add 100 in the equation. Okay, it's the same direction as our convention, so plus 100. And then we have 120 Newton here. So in this case, it is acting at certain angle with respect to horizontal axis. So I decompose this guy along its component. So we have one component, which is equal to 120 cos 30 degrees. The other component is 120 sine 30 degrees. Right? So we have here 120 cos 30 degrees times the perpendicular distance 0.4 plus 0.4 cos 30 degrees. So we have a moment due to the component of 120 along vertical axis. Then we have another component along horizontal axis, which will give us rotation counterclockwise, so we have minus sine 20 times its perpendicular distance, basically 0.4 sine 30 degrees. So we have MA. Okay, so this MA and the resultant at A can be used to write our final answer. So at A, we will have at A, or resultant at A, with this value and this angle. And then we have moment at A, which is 123.4 Newton meter. Okay, this is the equivalent force couple system at point A due to these forces and couple being applied here. All right. Any question about this so far?
On the previous slide, why we must minus 120 sin 20?
This one.
Yes.
Sine 20. Ah, my bad. It should be sine 30, right? Okay. Thank you for that. It should be sine 30 here. So my answer is wrong. It's busted here. What's the actual answer?
I got 152.39.
152.39. Okay, let's say we use your answer. 152.39. Next, we move to the second exercise. This one is talking about moment in 3D. Okay, so the first question is to find the moment of force F about point A. Okay, so this is our force F and this point A. So F is passing through point B and D. So the information on this F is given in terms of coordinate. So that means we can determine the moment of F about A by using that information. The moment at A should be equals to the position vector crossed with the force vector. And the position vector must be starting from point of moment. Since we want to know moment at A, so it must be from A towards the line of force. This is our line of force. Okay, so it can be either point B or point D or somewhere in between. In this case, point B is the easiest one, so I'm going to use that. So I'm taking RAB, which is equal to 0.1 and 0.2 I minus 0.3 K. Okay, so along X is 0.2, along Y is minus 0.3. Okay, from A to B. As for our F, okay, we can decompose this F along IJK. We know the magnitude is 700. This will be the unit vector from B to D. Okay, so along X, you have displacement of 0.2 positive divided by the length of this vector. Okay, basically 0.7. And then along Y, you have the motion from B to D. Along Y, it goes down. So you have minus 0.6 there over 0.7 J. And then along Z, from B to D, you have motion along negative Z axis for a value of 0.3. So we have minus 0.3 here. Okay. If you are wondering how do I get 0.7, 0.7 is actually equal to 0.2 squared plus 0.6 squared plus 0.23 squared. This, you take square root for the sum of this value. You'll get 0.7. Okay. Once we have RAB and F, we can calculate moment at A. Really equals to RAB cross F vector. Okay. When we do that, calculate, in the end we have MA equals to minus 180 I plus 0J minus 120 K. Okay. This is the moment at A that I calculated. Alright. The next question. Moment of force F about GA axis. Okay, GA axis, where is point G and A? So this is point G, this is point A. Okay. GA axis, meaning starts from G, ends at point A. Okay, and be specific with that. Okay, start from G, ends at A. Why we need to be specific? Because we know moment about this one. Okay, moment about GA axis. GA axis should be a unit vector along GA, lambda GA dot MA. Okay, lambda GA or unit vector along GA axis also start from G and ends at A. Okay, so unit vector along GA axis, start from G to A, the unit vector is positive K, since it is going through or it is acting along positive axis, so it's plus K. Okay, so once we have lambda GA equals to plus K, mGA or moment along GA axis due to this force F is just equals to, okay, before that, moment about GA axis is equals to lambda GA dot moment on top of any point along this axis. Okay, moment to this force on top of any point along this axis. So you have point A here, you have point G, or somewhere in between here. Okay, so you can use moment at A, at this point, or at G. And since we have calculated moment at A, we can might as well use that moment at A. So moment about G axis is equal to lambda GA dot moment at A. Alright, so moment at A is equal to this value. So lambda GA is equal to plus K. Okay, in this case I might change the order here, but it does not matter. You can write lambda GA first and then dot M, or in this equation I accidentally write MA first and then I dot with lambda GA. Anyways, still give you the same answer since we have dot product here. However, if we are talking about cross product, this is a definitely no go. You can't reorder the operation. However, for dot product, you can reorder the operation. It will still give you the same answer since we have dot product. So in this case, we have plus K here. So even though we have I here, so ignore the I term. Just concentrate on K term since K dot K will give you 1. So in this case, the answer will be equal to minus 120 Newton meter. This will be the moment about GA axis. Everyone is clear about this?
Yes, sir.
Okay. Pretty straightforward. And lastly, the question wants us to explain why moment about AC will be equal to 0. Okay. So to see it clearly, we can write the equation for moment about axis AC. So it must be starting from A to C. Okay, so moment about axis AC equals to lambda AC dot with moment of any point on top of the axis AC, right? So I can choose moment due to force F at A, moment due to force F at B, or moment due to force F at C. Okay, the easiest way to prove moment AC, moment about axis AC equals to 0 is to take moment at axis AC equals to lambda AC dot MB. Okay, so B is 1 point on top of axis AC, so B can be selected. So I'm taking moment at B. And if we expand this further, moment at B is actually equals to a position vector from a point of moment, in this case point B, towards the line of force. Now the line of force is also passing through point B, so I can write BB here. Okay, RB to B, and then cross with force vector. We know that lambda AC is not 0. Okay, we have a value for lambda AC. F is also not 0. We have a value for F vector. However, RBB is 0. Okay, a vector from B to B, vector from the same point to itself must be equal to 0. Okay, so that means this part is 0. So 0 cross F, you'll have 0 here. Dot product with another vector. So in the end, you'll have MAC equals to 0.